Sorry about that, guys. Well, I don't know what's up with that, but looks like it's kind of improving, maybe? Oh, I don't know. One day. Anyway, so today we'll be doing testing, and it looks like this is not doing its job. Alright, so today we'll be doing testing of our code, and please ignore the absolutely atrocious flashing video. It's probably a bad HDMI cable. Ooh, my god. That is an atrocity. Yeah, sorry about the video quality, guys. I guess we won't be doing face cam today, because that thing is just dying. But yeah, today we'll be doing student testers, and doing fancy testers, your own testers, custom testers. You know the drill. So, in doing that, okay, I'm just going to turn that off. So in doing that, what we're going to be doing is we're going to be using some new test frameworks and some techniques you might not have seen before. And these techniques are going to help you to test your code much more robustly, and they're going to help you test your code much better. But before we get into that, I'd like to ask if there's any questions, or if anybody has any questions about anything before we get started. So if you guys have any questions going in, now is a good time to ask. Again, today's topic is going to be advanced testing. Alright, seeing as there are no questions yet, we'll be going into first a bit of the concepts on the testing methodologies we'll be using, how they all work, what they all are, and what they're doing. So we're going to get into it by talking about unit testing, test coverage, and the flight recorder. These are three techniques which you'll see a lot in industry and a lot of how you actually test code in the real world, and these will also help you in assignment 4, because assignment 4 is going to be a competition. So in assignment 4 we're going to be competing based on who can have let's say the most solutions to a puzzle within a given time frame. So you need good time complexity, and you need to have a lot of edge cases covered, right? So in order to meet these requirements, we're going to have to be good at testing our code. Of course, you can still do well even if you don't. Sorry, I just want to turn on my overlay here and give another shot at the webcam capture, because maybe it's going to work. But yeah, so this is what we'll kind of need to get our assignment working well. Now, first thing we want to talk about is unit testing. Unit testing is the idea of testing small parts of your code one by one, and there's frameworks that help us do this. So unit testing is like, imagine you're testing all the little parts of your code. So like the mini testers we're given mini testers which sort of do little bits of our code one by one and are able to test whether certain methods work. And that's kind of how you're graded, and that's a really useful way to organize your tests so that you know what's failing. So we can learn how to make good unit tests today, ones that are similar to mini tester but maybe a bit more robust. We'll also learn about test frameworks, which are tools which help us organize and run our unit tests in a way that's predictable and robust. And we'll learn about test engines, which are quite closely related to test frameworks. These are all easy to set up, and I'll show you how, and this will help us do some unit testing. So let's just get right into it with those. But before we do that, are there any questions about, well, anything in general? Alright, so now I'm going to go about setting up our test environment. We're going to create a new project, and we're going to do it in an unusual way. So we're going to go File, New, Project, and this time, instead of just doing a regular Java project, we're going to click Gradle. And we're just going to keep everything else default. Go next, and I'm going to call it test demo. Or maybe I'll call it, super tic-tac-toe, because we're going to be doing some tests on tic-tac-toe on our old hash table. I'll put that in a new window. And now we have a new format for our project. There's some files we don't recognize, like build.gradle, which we can for now just ignore. But as it downloads and unzips everything, we should eventually see that folders are generated called our source folder and our test folder. And this is going to let us greatly improve our organization in terms of our unit tests. So this is how we professionally build tests. If you look at Best of Comp from last year, our showcase of all the best submissions, you'll see a lot of people used these unit testing techniques in their testers. And I'll show you why they're useful. But before I do, I'll tell you about it. One of the most useful features of this test technique is that it allows you to run tests one by one. So it allows you to make assertions, which are basically telling your computer what you expect the output of your test to be. And the computer will then fail or succeed the test depending on the output. And that will be a very useful tool because it lets you guarantee that your program is outputting what you want. It lets you run individual tests one by one. So instead of like in the mini tester where it runs every single test every single time, and you might not be sure where you're failing. This one, you can literally click the run button next to each individual test, which is very helpful. And it also supports a very easy cleanup and setup, which is called before each and after each, which lets you set up the environment for your test. So for example, if you have an object which needs to be set up before you can use your method, you can set it up in the before each, and then it'll be set up the exact same way for every test. So it lets you save a lot on how much code you write and write much more efficient tests. And of course, it gets more useful the more complicated your program is. So now I've generated my code, and you see in my source folder, and I have a main and a test. So I've got a main folder and a test folder. In my main folder, I can just kind of put in my same code as I had before. So I'm going to open in Explorer, and I'm going to put in the code I made from previous sessions. So we've got main Java. I'm just going to go into my idea projects. I'm going to go from my hash map. It's called hash map, right? Yeah, my hash map and my tic-tac-toe. I'm just going to copy paste those files in. So it's going to be under super tic-tac-toe, source, main, Java. Just going to paste that into there. And of course, I'll also take my tic-tac-toe, source, all of these, go into there. Super tic-tac-toe, where are you? Here you go. Source. No, this goes to main. And this goes into Java. Okay, so now I've got all my code here in source, main, Java. If I want to make a test for the code, I could run tic-tac-test here, or for any method in my thing, I can just say right-click on it and generate test. And this will automatically write a test for this code, or it'll automatically put the header here. So the test class will basically, it'll put a new Java class inside of this test folder, which will create tests. But since we already have these tests, kind of, right, we can actually move these on over. Let's do that. So we've got a couple methods in our tic-tac-toe game here, which could be subject to testing, like horizontal winner. So I'm going to right-click it. I'm going to click generate test. Okay, and yeah, do we want to set up and tear down? Probably not. Let's just do a simple example for now. We'll just go tic-tac-test, tic-tac-toe test, and now here we can have a test case for this specific part of the code. So we can say tic-tac-toe, generate test, and we want it for horizontal winner, vertical winner, and diagonal winner. Okay. Okay. And now we have these tests. So let's see how these are different than just having our tests in a .java file. When we have our tests in a .java file like this, we have our methods like test diagonal wins, and we can't run them individually, right? So we can only run them as part of a main method. So when we add more tests, we also can't easily run them. And we use things like print lines to debug, which can get messy because you're not sure which test each print line comes from. So instead of all that, what we can do is we can put these methods into our test class. So first, let's copy paste all of our static things here. Boom. Boom. Right, because these static fields, these can stay the same. These are just our board configurations, like though known wins and known loses. This is just kind of what we're testing based on. If you remember from the first time we wrote this, we wrote out all these board states, which just determine whether the game should be won or lost. And I'll just copy paste these into the code so that we can access them. And then I can modify my old tests. I can say, instead of all of this, test vertical wins, well, let's put that into here. Tic-tac test, vertical winner. I can now say, wait, is it assert null, vertical winner, winner start ver. Or I guess assert not null. Assert not null. And it's going to be vertical winner, tic-tac-toe dot vertical winner, winner start ver. Right, just like this. And now I can kind of use this much more concise format for my assertions, right? So I can, instead of having this long print line, which is ambiguous and not very good, I can just have winner middle vertical is null, so this one should not be null, so I can just, boom, get rid of that. Winner end ver should not be null, so we'll just take that, boom. Ooh, boom. So start like this. And now we can do the assert null, so we can just change this to assert null. And now this will allow us to much more concisely test our code. So assert null here should be vertical winner, no win. And this one as well with all null. Let's do that too. So assert null, all null. Boom. Boom, boom. And now we have a complete test, but it's also much shorter than it was in the other one. So if I put these side by side, we can see the difference. The standard test, as we normally write, has 3 lines per thing, and it's kind of ambiguous as to what happened. And now we can see that with this test, it runs individually, it has much shorter syntax, and if it fails, we can know exactly why it fails. So it's quite helpful in that regard. So here it passed, but we can actually see the details on that pass. Or if we, let's say we make it fail, so we can say assert null by accident, assert null. Right now we can watch it fail, and we can see what it looks like when we fail a test. When we fail a test, it'll tell us exactly why it failed, and it'll tell us which line it failed on, and it'll give us a lot of details. It'll show us the difference between the outputs that we wanted, and it will help us a lot. So this was a basic example of how these tests can be set up to be easy. Now we can also easily set up the same thing for the other win conditions, such as all of these. So again, we can do those assertions. I'm just going to skip that for now, because I want to get into some other test techniques which are very useful. Actually, you know what? I won't skip it. I'll do it properly, but I'll just do it the lazy way. Copy, paste, horizontal or diagonal winners tests like this. Copy, paste. Now I'm going to replace if it equals null with the correct thing. So again, we want to assert null. Assert null this thing. And we want to assert null this thing. Very simple, right? And we can assert anything. We can assert null, we can assert the two things are equal. Assert just means that if this is not the case, it'll fail the test. So now we can assert not null this. And I'm just doing this, I'm going to do it relatively quickly so that we can finish with the JUnit part and we can get to the next important parts of our thing on testing. Here we go. Assert not null, and of course, assert not null. Or was it assert not null? Yeah, I actually got these the wrong way around. Assert not null, assert not null, assert null, and assert null. And this one should be all null. Alright, so I'm converting this test to this format. I gotta do the horizontal winners as well. Bada boom. Bada bing, bada boom. Horizontal winners. Alright, so this is a bit dry so far, don't worry. Assert not null, because we're going to get into some more advanced techniques in a second. I just want to set everything up with JUnit to make sure that everything works nicely and is pretty. So boom, boom, and the same for these ones. If horizontal winner, this one should be, it should not be null. So winner middle hor and winner end, or middle and winner end. There we go. So now we've got all of our tests, and we can just run all of our tests like this. We can run tic-tac-test, and it's going to run every single test we've set up. Here it passed all the tests, which is fine. Now we want to figure out how good our tests are, which gets us into the next stage of our session. So if I turn back my slideshow, oh yeah, we can use this testing technique for things like testing APIs and continuous integration. Those are things that are beyond 250, which you can read about. But now we can get into how we can figure out if our tests are good. It's called test coverage. Now, test coverage is probably the most important thing we'll be covering today. This tells you about how good your tests are. It's how much of your code is actually being tested. It's a way to empirically tell you how good the tests you wrote are, essentially. Test coverage will tell you how much of your code the tests are actually checking. So if I look in here, I've got this tic-tac-toe test, which is my JUnit tests. If I run this with coverage, it's going to tell me how much of my code is being tested. So I'll click this button here, run with coverage, and it'll tell me that I'm covering 25% of tic-tac-toe, 0% of tic-tac-test, 0% of hash map, and 0% of AI. So this is showing me how good my test is, essentially. And if you did this on Minitester, hint, this is very similar to how a Minitester looks, this tic-tac-test, you'll see that it only covers a small percentage of your code. So this is kind of how we identify what the weaknesses of our tests are and what we should be improving. So now that we know that we should be improving, well, this part of our tests, we can see that we need to be, well, writing more. Specifically, we need to write more in terms of tic-tac-toe and especially AI and hash map. So let's go about improving our test coverage. Let's find some parts which are not covered. You can see they're red. And let's identify how we can cover them. Let's say hash map, for example. So since hash map is completely not covered, let's maybe write some tests which will cover hash map. So an efficient way to do this will be to right-click on a method. Let's say which one here is red that we think would be easy to test. I think the constructor would be an easy one to test. That one is red. It's not covered, right? So we can create a test for it. Hash pair. All of these, there's a lot of methods, right? But we can just do the constructor. Or is there even a constructor in this class? Public hash map. Oh, there's not. Okay, so even easier. We can just cover, let's say, put. So we can generate test. Hash map test, let's call it. And actually, we can just generate test stubs for all of our various methods except for main. And we can also do a setup. And why don't we do a teardown as well, so to demonstrate those functions. So now we have a bit more of a test. Before each code, this code runs before the tests. So before my put or remove or any of these tests are called, this runs before each test, and this runs after each test. So this kind of destroys your objects, and this kind of creates them. So if here I have, let's say, a static hash, or I'll just call it a hash map, string integer map, and this one will say map is equal to new hash map, and teardown will say map is equal to null, right? So this sets it up, and this tears it down and resets it to be how it used to be. Let's maybe also say we have a stack of strings, let's say tests, or even easier, instead of making a stack of strings, let's just make it an integer, and we can generate random integers. That would be pretty easy. So you don't need stack. Now we can say, for example, for put, we can say map, let's say map.put, or let's actually say integer key is equal to random or new random dot next int, integer value is equal to new random dot next int as well. And now we can say map dot put key comma value, and now we can say assert equals map dot get key value, right? So this is basically testing. Is our hash map always doing the right key and value? And if we want to make this test a bit more robust, we can say, let's say, do it for 5 seconds. Long start time is equal to system.nanotime. And then we can say while system.nanotime is less than start time plus, let's say, what is, actually, let's do it millis. The current time millis. I'll just do it in milliseconds so it's easier to do the math for how many 5 seconds is. System.current time millis. It just does a 5-second stress test. 5,000 milliseconds will be 5 seconds. It's going to be a long test, huh? But it's okay. And now it's going to do randoms. And in fact, if I want to make it a really good test, we want to have a consistent random seed. So we can say static random rand is equal to new random, and I'll put some funny seed. And now we know that no matter how many times you run this, the test will be the same, so it's repeatable. We'll say rand.nextInt and rand.nextInt. And every time we set it up, we want to say that rand is equal to a new random because we want to have it reset every time we run. So it's repeatable. A bada bing, a bada boom. And we'll even make it null here. So we make sure setup will set it up, and tear down will tear it down. Okay, so now we've got our various things set up, and we can test our put. So if we run this test, we can hope that it always passes, because if not, the hash map is bad. and it's going to run for 5 seconds, and this is going to take forever to test. But yeah, it looks like it passed after 5 seconds, so for 5 seconds it randomly stressed it out. So this is an example of a test for put. For remove, we can also say, do a similar thing, right? Because we already have our before each and our after each, so all of these things are already set up. So instead we can say map.put key value, map.remove key, and now we can say assert null, map.get key, right? So now we're saying that whatever we added better not be in there, right? Or actually here we can say, right, we can say that make sure it was added and then make sure it was removed. Added, and here we can say make sure it got removed. Right, and now we can see our test coverage going up. So if I rerun, if I run hash map test with coverage, we can see how we now have more coverage of our code. We'll wait 10 seconds for it to run because it is a very robust test. Replace active suites. Now we can see our hash map is covered 62% for methods and 59% for lines. And if we go in here, we can see that our put method is now almost completely covered. We miss a few edge cases, and we can actually see which edge cases our tests miss. So here we can see that the edge case of having a collision is missed. And we can see that the remove key K is also not very covered, which is weird because we did cover it. So maybe it just didn't run. Yeah, we only tested put, so we'll have to do the whole class. And now that should update our coverage. Replace with active suites. Oh, that was tic-tac test. No, I want to do hash map test, all of it. Wait, run hash map test with coverage. Sorry. We're just going to run the whole test rather than just the put test, and we can see how much more we cover. Bada boom, bada bing, and it says which one it's testing right now. And we've ran remove. Now we're testing put. And we'll replace our active suites. And we can see that our hash map is now 75% covered. We've covered our remove method except for this one edge case. Or actually, no, we just never touched this bracket. We've covered our remove case or we've covered our put except for this edge case. So we can actually identify that parent list equals value. So collisions are not being tested. Right, so that's one part we're not testing. We're also not testing our contains key because it's red. Right here that's how we tell. And we're not testing our main method, which is fine. And we're not testing our getting a null key. So now we know which edge case is a test. So now I can go back into my tests and I can say, okay, so we need a test for contains key. Let's do that. Here we've got contains key. We can just basically copy paste our test from our put. And we'll say, for example, assert true, map.contains key. Right, now we can make sure that it contains every possible key. And we can also say, for example, another test for contains key. Let's say assert does not contain key. Right, and now this one will say, instead of putting some key, we'll say key plus blah, blah, blah. And then we'll make sure as well, or assert false here. Map.contains key is this. Okay, and now we will, just to make sure this test is good, because it's going to test it for 5,000 seconds, it'll probably actually accidentally have this key inside. We'll also just say map.remove key plus 949. So now we can really robustly test our code. And if I run my coverage again, we can make sure that our contains key is actually tested. It's going to take now, 20 seconds to run because I've added these tests. And you don't have to do these 5-second tests. I just like them because they're kind of like what CodePost will do. Well, no, CodePost does a more time complexity tests like this, but still, 5-second tests could be good. So now we can run it. Does not contain key, bada bing, bada boom, let's go. Testy, test. And eventually we get our results and we can see our coverage should update. Did I run that with coverage? I better have. Yeah, now we're up to 87% of the methods. Contains key is passed. And we've tested basically everything except this one edge case where there's a collision. So we can just make a special test just for that edge case. And our hash map will then be robustly tested. And we know it's robustly tested because we can see that our coverage tells us every single method is tested fully. So we can say void test put edge case. And now we can say, for example, map.put that, comma 21, and now map.put, well, actually we have to have something that hashes to the same value, right? So that's a bit challenging. How can we make sure that it hashes to the same value? Could we say map.hash? Yeah, we could actually. So we can access the hash method here, and we can get something that also collides with that. Let's see, hash key k, k.hashcode. Okay, so where is it? Put, it's if there is a list in there. Yeah, okay. We know we can't use the same key because that's going to override it. We have to have a key that hashes to the same but is not the same. So if I go into my hash map here, I can force that to happen in my test by saying map dot, what is it called, our load factor. Let's just make those not final. Static double load factor. Let's just make our load factor really high. Equals 99999, right? So it's not going to care how much stuff is in our map. Let's just say our map's linked list will be of size 1. Can we make one initial size? Yeah, I'll add a constructor for this too, just because you know, we can, and it'll help us get this edge case. Constructor size. If we wanted to do this, we could extend the map class as well, but I'll take in as input a. Actually, you know what? I'm not going to bother with that. I'm just going to set the load factor really high, and I'm going to hope that doing a 5-second test will actually do it properly. So, boom, boom, bada bing, bada boom, and we'll make it a really small maximum here. So, or actually, do we need to? No, we'll say long start time. Okay, so now I'm going to do a very similar test of put, except it should now hopefully test the edge case. And if we run it all with coverage, let's hope we get it all, and then we can determine that our test was actually objectively very good. So it'll run for a little while, and now while it runs, afterwards we can confirm the coverage. We can get into a bit more of the theory on coverage, so a quick slide to go over it. Coverage looks like this. We can run with coverage by clicking the little shield button at the top near our run. That will tell us how much of our code was tested. We can see the coverage by seeing the colors to the left of our methods, which tell us how much of that method was tested. We can see also percentages, which refer to how much of our code got covered by our tests. And again, we can use coverage, for example, in the mini tester to see which edge cases are not tested, and then we can also write tests for those edge cases. So now, test coverage, of course, I think that's honestly the most useful thing we're covering today. And now we can also get into stuff, we're into the debugger. It looks like our 88% methods is pretty much as we'll cover. I'll have to go through a lot of effort to test this, so I'll say it's not worth the effort. I'll leave that as an exercise to the reader. And of course, our main method is not covered, but I don't really care for the main method being covered because, well, it just puts the bmovie script into it. Who cares? As a utility class, most of it is checked, except putting in null key is not checked. A couple edge cases and put are not checked, but we know that from our coverage. And we also know that none of these methods are covered, and that's okay. We'll write those tests. Well, you can write those tests if you'd like to. We can write them as we wish, but that is how generally this thing works. Now I'm going to show you a few breakpoint tricks, which I find very useful, and hopefully you'll find them useful too. And these can help you learn about your loops and your time complexities and everything. We'll get to that frame or that JFR later. Now we're going to show you a bit more of the advanced debugging techniques. Alright, so the first thing I'm going to tell you about is overhead, and the other one is called memory. And I'm going to show you a bit more robust things on breakpoints as well, which will help you test your code. So let's say we have something in our code which is looping a lot. So an example of this would be our tic-tac-toe AI. Our tic-tac-toe AI does a lot of looping, in min-max especially. So if we run tic-tac-toe, and we want to see just how much it is looping, we can actually just put a breakpoint right here. Let's just say we have a breakpoint every time it calculates the terminal state. We right-click it, and when we right-click a breakpoint, we get a lot of information. So again, this is from AI. This is from the tutorial from Tuesday. We can see by right-clicking the breakpoint, whether we enable it or disable it, which will enable or disable doing anything on the breakpoint. But we also have this check mark for suspend. If we enable suspend, this will behave as we expect. So if I run tic-tac-toe, which is over here, tic-tac-toe, if I debug tic-tac-toe with this, and I enable the AI, so if I give it the arguments, which let it use the AI, give it a second here. Allow access, boom, and I tell it that we have one player, and we go some coordinate. Okay, now the AI has started, and if we enable suspend, we'll see that every time we hit this line, it's going to pause our program, right? And that's kind of what we want from the debugger sometimes. We want to pause it. But what if instead of pausing it, we basically want to do the same thing as a print line? Then what we can do is we can uncheck suspend. We can go to overhead, we can click next, and now it's actually going to tell us how many times this method got called. So it looks like min-max is being hit a lot. This specific line has just gotten hit like 4,000, 5,000 times. And the only thing it's doing right now is calculating the game state. So we can see that we are going through a lot of possible game state. It's going to go through every possible play of tic-tac-toe, and wow, it is surely taking its time. So it's hitting this breakpoint a lot. If we want to look at something like time complexity, we can look at this breakpoint compared to another one. So let's say how many times do we hit AI.minmax compared to how many times do we hit, oh, actually I'll put this right on the method header, right? So how many times do we hit AI.minmax versus how many times do we hit find best move? So how many times do we hit, like what's the ratio? So if I run this with the debugger again, and I give it the same arguments, we can see the ratio of how many times does it try to find the move versus how many times does it evaluate the board. So if I go to console and I go put in my arguments, how many players, 1, specify x coordinate 0, specify y coordinate, come on, 0. Now we can actually see as it counts up. So we've hit find best move only once, and that has hit min max so many times. Like the time complexity of this thing must be terrible, right? Because you find the best move once, and you do the min max. What is it, like 20,000 times? Now it's going up. It's going up. I don't believe this infinite loops. I like tested this earlier. I'm 99% sure it works. It's just gonna do this like a lot of times. So this is one way to also to check where we're looping. So we know we're not looping in find best move, and we know we are looping in min-max. And again, what I did was I put a breakpoint, I right-clicked it, I unchecked suspend, and this lets me see how many times each piece of code runs. Now, damn, that is taking forever, and I'm really hoping it doesn't freeze. But it's looking like it's slow. Let's just make sure tic-tac-toe actually works. With one player, I'm going to say 0, 0. Yeah, it works, right? So it's just looping that much because that's how inefficient this algorithm is, right? And, well, that's the first advanced debugging tool we have. The next advanced debugging tool I'll show you is a conditional breakpoint. A conditional breakpoint is like a normal breakpoint, but we can actually check based on certain values. So, for example, if we have a null pointer exception somewhere, we can actually check, put a breakpoint if that thing is null. So let's do that right now. Let's just say that our opponent, instead of... actually, where can we do this? Let's do it here. Let's remove this null check. If we don't have this null check, we can see that our game is going to have a null pointer exception. But it's going to null pointer exception only sometimes, right? Because it's going to null pointer exception if and only if that thing is actually going to be null. So if we do one player, we start on 0, 0, we're going to get a null pointer exception. But we don't know when this null pointer exception is going to happen, because there's a lot of times when this happens and it's not null. So we only really need to freeze our program if this value is null. So if I put a breakpoint here, I click more, and I have a condition, I can say b at row 0 is null. Done. So now we've got a conditional breakpoint which will freeze here if the board at row 0 is null. And if I run with the debugger now, and I set up everything again, because this thing takes arguments as to how many players and everything, so we're going to have to do that first. So how many players? 1, x coordinate 0, y coordinate 0. Now this breakpoint will only stop if b at row 0 is null. So now we can see that this is null. We get to the breakpoint again. Well, we've already had a null pointer exception. But this way we can see that this style of debugging, this conditional breakpoint, it lets us put a condition on when the breakpoint stops, so that if the breakpoint is null, for example, we have a null pointer exception, we can debug that more easily. If I set to this thing is not null, we can see that it also works. So now it's only going to pause when that value is not null. Now again, this is super useful because a lot of times we write big recursive functions which go through a lot of lines of code, and they might run 1,000 times before we have an error. Well, if we do this, then we'll actually only pause it once we have an error. So see here, we pause when this thing is not null. B row 0 is not null, it's false. So here we paused, and we're actually never going to pause when it's null. So we can see we're going to get that null pointer exception. But yeah, so that's what's called a breakpoint condition. You add those again by clicking more, and then checking off condition, and then you can put whatever you want. So here I put B row 0 is equal to null, and bam. That's conditional breakpoints. Those are super useful. Those basically breakpoints on steroids. And if we look at the more options as well, there's a lot more other useful things. You can remove the breakpoint once it's hit, not that useful. Put a message, not that useful. But yeah, the most useful one is the condition checkpoint. And of course, the suspend. So if we don't want it to suspend, we can actually see how many times do we go by this thing when it's not null. So we can combine those two things. We can combine conditional and suspend. And of course, let's also just make sure it's not null. So when we do these, we normally want to check that it's not null and it's not the opponent or the player. So else if b row 0 is not null and b row 0 is not null and okay. So now we've fixed those conditions, and if we rerun it like this with the debugger, and I've now got a non-suspended breakpoint with the condition, I look at overhead. Well, first I have to look at console. We can actually see the exact number of times that it's passed this while it's null. And if we want to, we can put two breakpoints, one where it is null and one where it isn't, and then we can compare how many times is it null compared to how many times is it not null. So 0 and 0. Now I go to overhead, and I can see that this conditional one, it's null very little of the time. So, well, actually, let's put a breakpoint here where it's not null. So don't suspend, and condition is that, oh, actually I have to put this breakpoint somewhere else. So let's put it here. Boom. Actually, let's not bother. Let's just put a breakpoint here, and let's say all runs versus not null runs. So, boom. Okay, we want to go 1 player, 0, 0. I just put 1, 0, 0 as my default thing. Now we can see that it's null, which is line 29, which we can actually like put a label on if we want to. But yeah, null line 29. It's being hit 270 times versus 800 times for when it is total. So we can see that it's null right about 1/3 of the time, right? Which is, I don't know if that's a useful statistic, but here we can show how conditional breakpoints and no suspend breakpoints can be combined to show you, like, let's say, what proportion of the time is the thing null. So what proportion of the time is B at row 0 null? Well, we know it's null when it's null here 865 out of 2,500 times, and we know that min-max runs like 50,000 times for each time it runs find best move. And these are the kind of things we can learn with the advanced breakpointing techniques, which we can learn today. So that's some of the advanced breakpointing so far. One more advanced debugging tool I'll show you is memory. We don't actually evaluate memory complexity, but sometimes it can be nice to see where the objects we can create actually go. So if you want to see what lives in your memory and what is taking all of it up, if let's say you have an out of memory error, you can click the memory tab. We can stop at a breakpoint or just click the pause button, click load classes, and we can see what's taking up our whole memory. So we can see here we've got a lot of strings, and we can see what those strings actually are. It looks like a lot of internal Java things, a lot of IntelliJ things that we don't care about. We can see we have a lot of bytes, which we can't learn much about. And we can see we have a lot of hash map nodes, which makes sense kind of because here we've got a lot of, well, hash maps, I'm assuming. And we're using hash maps, I believe, in some of our evaluations, or it's just a built-in IntelliJ thing. But we can see what's basically taking up all of our memory. And if we have a situation where we have a memory leak, let's say we're trying to use dynamic programming, we can see that our memory will fill up, and that is that. So yeah, we've got our memory section, we've got our overhead section, and through that we can tell what is wasting all our memory. We don't have a memory leak here, so we don't have that problem. But if we did have a memory leak, this is where we'd be able to identify it. And you can identify it just because whatever's at the top there is probably what's causing your memory leak. And if you double click on it, you can actually see what is taking up your memory. All right, so those are kind of our useful debugging tools. We've got our memory view, our console view, which we're familiar with, and our overhead view. And of course, we've got our stack over here, like a call stack. And all of that together should help you evaluate infinite loops and evaluate your time complexity and everything far more effectively. Now, when it comes to testing time complexity, I'd say there's a two-step process. If you want to see the time complexity of your method, you can try using the speed tester, and you can also glean some information from using the breakpoints thing. Thing is about the speed tester is it'll factor in time complexities of everything. So you might put counters, and you might not realize that some method you're calling inside is O of n, right? So counters are not perfect. You might be calling some O of n method inside of your code, which would make it, an O of n factor longer. So the speed tester is useful because it just tells you the fact, like it tells you exactly how fast you're going. So that's what we recommend for testing speed. But you can also learn a lot about your loops from using overhead. All right, now the next technique we already know about. It's called using the speed tester. That there's separate videos on. But now we're just talking about things we haven't covered. So I'm assuming you guys know about the speed tester, but that's a useful thing as well. All right, now we can get into our final and maybe our most exciting feature, which is called the Java Flight Recorder, which gives us a lot of insight into how our code works. But to use our flight recorder, we actually have to exit out of our nice new test class in IntelliJ Community Edition. Let's terminate all those. Boom, 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 boom. And we're going to open up IntelliJ Ultimate Edition, because this is a feature just of there. And again, we get Ultimate Edition for free, so this feature is just going to be one little taste of the more advanced functionality we can get if we use that. And this is also available in Eclipse, but we'll not cover it because it needs some plugins in Eclipse. But if you're a diehard Eclipse fan, you could still do it. You just need to download some plugins for Java Flight Recorder. Okay, so now I'm going to open my project, Sasha, idea projects, where is it? And it was called Super Tic-Tac-Toe. I'm going to open that up. And now it's going to be open in the Ultimate Edition. And here we have another option in our run configurations compared to before, which is called Run with Java Flight Recorder. Let's trust the project. Next tip, close. Okay, so now we've got what's new. We don't care. We just want to see the source. All right, let's let it index first, and then we can do it. But the button we're going to want to push is going to be this one, Run with Flight Recorder, or Run with Java Flight Recorder. And once this thing loads, we will be able to do that. Let's just let it build first. And with our flight recorder, I can run, for example, our... what could be a good one? I think the Tic-Tac-Toe AI is a good example because it's quite slow. And we could also use our snake game as the flight recorder. Oh, yeah, I'm sorry. I am showing the wrong screen. Yeah. So what I did was I opened up IntelliJ Ultimate Edition, which is... yeah, thank you for the catch. I opened up IntelliJ Ultimate Edition, which is just a different version of IntelliJ. Make sure you're on the Ultimate Edition, and there we can use the flight recorder. I just opened my project, so not that much was done. I just did File, Open, and then my project. Same project as before. It was the Super Tic-Tac-Toe. And now I just open it, wait for it to index, and I'm able to use the Super Tic-Tac-Toe class with the Java Flight Recorder to see how it's running. Let's just let it finish updating the indices. Now it's done. So now if I run something like Tic-Tac-Toe, and I run it with Java Flight Recorder, and let's put it as 1 player, 0, 0. It looks like it's not doing much, right? Let's put 2, 2, put 2, 0. I'm just playing against the robot right now, right? And one of them 1, and we reset the board, and yada, yada, yada. We don't care. What we care about is the profiler side. So if we stop profiling and stop, we can actually see what was using our computer and how much it was being used. We can see our call stack here. This is not too useful. We can see our call tree, and we can see what was running the most. So we can see that we run our main method, and of the main method, we wrote a lot of min-max. So about 25% of our time we were running the min-max out method. The other time we're running the scanner method, and we can see which methods are running when. And this will help us debug our time complexity because we can see exactly which methods are called from where, and which ones like loop more, which ones take up more CPU. We can see our CPU timeline here, what takes up what. It's kind of blank right now because not much happened. We can see our Java events, which are much more advanced. We don't really need to get into that. But yeah, we can also see which methods took up the most tasks. We can, and if we enable more settings, we can actually get more information. So if we go to our profiler, we can view a lot of things. But most importantly, we can view what methods took up time, basically. If we run this again, we can change our settings and we can get more information. So if I go to my profiler, I can go profiler home, attach it to tic-tac-toe. And I'll go in my settings here. And I'll enable a deeper level of insight. So I'll go to Bill, or where is it? Java Flight Recorder somewhere. Profiler. Java Flight Recorder, and we can go profile to get more information. And we'll run it again. So I just changed my setting there to have more info. Put 1 player, 0, 0, let's say 2, 2, 2, 0. Just playing the game, just using my app as normal. I stop the profiler. And now we should get a bit more info. Let's just close all the old ones, huh? 8:51 a.m. Here we go. Now we can get a lot more info in our call tree. We can see our flame graph, which is basically what runs. Here we have a pretty simple app, so not much, but we can see that min-max is running a lot. Min-max is very high up on our stack, and we can just see which methods get called more, which methods get called less. We can see our call tree, but this is not the super important part. We can see tic-tac-toe main runs a lot of min-max, and we can see the percentages are how often that runs. So 7.5% of the time it runs that. It usually goes quite deep, and then it gets less and less frequent as time goes on. 3%, 1.9%, basically never happens after that. And then we also get our method list, but also if we run it while we're running, boom, boom, we should be able to see our various info real time. So if I go to profiler and I go home and I attach it to tic-tac-toe, why is it not giving me my live insights? That's interesting. Settings, view mode. Yeah, give me 1 second. I'm gonna make sure, because in my version on my non-virtual machine it does it better. So let's see, memory use, flight recorder. IntelliJ, just making sure that it's all proper. Analyze. Okay, so that should have the option to do live charts. Let's see why it's not. Oh, here it is. CPU and memory live charts. So now we can see exactly what our various methods are running, how much memory they take, how much CPU they take. And that's also useful just to see like how different actions in our app affect our app usage. So we'll put it at 0, 0. We can see that our CPU usage, did it take a spike? Yeah, it took a bit of a spike when we actually input it, our AI. And this is better than Task Manager because it doesn't actually include a lot of the other nonsense. So if we just run Task Manager on it, we could see a lot of stuff IntelliJ does, a lot of other useless stuff. Here, we can see only what our app is doing, nothing from IntelliJ, nothing from Eclipse, just our app. And we can see how much resources the app specifically is using. And we can see how much memory it's using, how much heap memory, how much stack memory. Well, yeah. So our heap memory and our stack memory is here. So we can see how many objects are on a heap, how many objects are on our stack. And we can actually watch as we do different things. For example, if we have Stack Overflow, how our stack memory could spike up and how that could affect our app's performance. So that's the flight recorder. It has a lot of other features. If I go into my flight recorder here and I stop profiling and show results, again, I can see how much each method was run. So here it's running a lot of internal methods, which is not that helpful for us to know. But it tells us essentially how much time was taken up by each thing. Again, it takes up how much each thing ran as well. Here it's mostly doing some thread stuff, which is just internal Java stuff. Again, it tells you a lot of internal Java stuff, so it's not that useful until our app becomes very inefficient. But generally it's quite nice and quite helpful, especially if you're doing the competition for assignment 3 and you want to see which part of your code is taking up the most resources. And that again is for IntelliJ Ultimate Edition. And the other features are all available in IntelliJ Regular Community Edition and in Eclipse. And that should be that. So wrapping up today, we had a few test techniques which I showed you. I showed you unit testing with JUnit. So what that looks like is this, where we have our unit tests under our test folder in source when we create a Gradle project. And here we can test how good our tests are using coverage. But our test will have a before each and an after each. The before each sets up our variables. The after each destroys our variables so that our actual tests can be very short and concise. This is a very easy and nice way to organize your tests, and it can make them very professional looking. Then, when we want to check how good our tests are, we can go hash map test, for example, and we can do it with coverage. And coverage is, of course, the next part of our slides. Coverage will tell us how good our tests are. So with coverage, we can know how much of our tests actually tested our code, how much of our code ended up being tested. It's kind of an indication of how good our test is. So after I ran with coverage, it's still running here. With coverage, it's going to take a little second. It should take about 30 seconds to run, right? Because it's doing 5 seconds per test. After it runs with coverage, we should have a view of what our coverage looks like. That will look like a percentage near all of our methods and our red and green lines, depending on what is covered. So here we can see that our hash map is 88% covered, which is pretty solid. We look at main, Java, 33% class is covered, hash map is 88% covered, and in the class we can see the red and the green. Tells us which edge cases are covered and which are not. That's probably the most useful thing for today. It's called coverage. Then, after we talked about coverage, we went into talking about our Java, or then we went into talking about our debugger and its additional features. Here we've got overhead and memory. Those are the two things we talked about. Overhead with silent breakpoints allows us to see how much our methods ran. So if I go into AI here, I've got my breakpoints, conditional breakpoints, which have a condition as to when they will trigger, non-conditional breakpoints. And I have suspend not checked. So suspend not checked means that the program will not freeze when it hits the breakpoint. Instead, it'll just increment this counter. So when I run with the debugger and I'm trying to run, not hash map test. No, I don't want to run hash map test. I want to run tic-tac-toe. When I run tic-tac-toe with the debugger, we'll see that these silent breakpoints don't freeze the program. Instead, they just increment a counter. So if I pass it my arguments, yeah, this is going to take a second. Slow computer, sorry about that. This is going to take a second, but once it does, we'll see that these silent breakpoints will let us count how many times each thing runs. So I'll have one player, I'll start at 0, 0. And now, if I look at my debugger, and I look at my, where's my overhead, we can see that it's running this a lot, and it's running that a lot, right? So find best move ran once, terminal state ran a lot of times. And when it's null, so line 29 checks when this thing is null, it ran about 1/3 of the time it's null. And 2/3 of the time, which is this unconditional breakpoint, it was not null. So that is overhead. Memory is similar. We can just view our memory here, and we can see what is taking up our memory if we have a memory leak in this thing. So we have to pause the program, load the classes, and we can see what is taking up all our memory. So those are our two things. Overhead and memory are our advanced debugger features, in addition to conditional breakpoints and the suspend checkmark. So that was our coverage on the debugger and advanced debugger techniques. Then we also talked about one bonus feature, which is in the Ultimate Edition of IntelliJ and with a plugin in Eclipse, which is called with the flight recorder. And the flight recorder lets us see how probable it was that a method was called. It lets us see our memory and our CPU usage. It lets us get deeper insight into how our program ran. So with the flight recorder, we can actually view how fast our program is running and exactly what was taking up resources, how many resources are being taken up. The flight recorder is much more of a professional tool. It's for when you have a lot of a complicated program and you want to see how fast it's running, which might actually be the case for A4, where we have a competition on how fast it can go. Now, I will actually show you one final example of the flight recorder, which will be using my local system. Sorry, I don't have it set up on my virtual machine, so you guys are going to have to deal with very small text. But this flight recorder example could actually be rather cool, I would hope. So if we look at it here, I'm just going to change my screen share around to make it proper. Boom. Goodbye slideshow. Goodbye win capture. Now you should see a big old display. And here we've got our snake game. If I run the snake app with the flight recorder, we can see our snake game here. I check off use AI and I reset the board. And I open our profiler. I go home, I go snake app, CPU and memory live charts. Wait, give those a second to come up. You can see we're using a lot of heap, a lot of CPU, and we can see that if we, for example, turn off the AI and reset, our memory is going to plummet to, or our CPU is going to plummet, our memory is going to plummet. We're basically using nothing without AI, right? Now, if I turn on AI, I reset, we can see suddenly that our memory usage is going to go way up, and our CPU usage is going to go way up. right? We create a lot of objects, we move around, our CPU and our memory usage goes up. Now, if we want to see what's taking up all our memory, we can go into our profiler here. I'm actually going to zoom in on this for you guys. Display capture. Let me zoom in on that even more. All right, so in here we can see our CPU and memory usage. If we increase our depth to, let's say, 15, and our size to 150, 150, so we're just doing a massive game right now, we can see how our memory usage is going to just skyrocket. Reset, and our CPU usage is going to skyrocket too, or it should at least. Right, so our memory is going to go up, our threads might go up, but you can see our resource actually didn't go up that much, but it should. We're at 15 depth right now, so we can see that our resource allocations should be increased. At least our memory should spike higher now. 534. It's not spiking that much higher. It's probably because it hasn't actually reached the full depth yet. But we can definitely see that our app is not that efficient, and AI is taking up a lot of resources. If we turn off AI, our usage just goes way down. All right. Now, if we actually want to see what's using our memory, we can go over to here. We can show profiling results. And here we can see, let's say, our method list. We can see that try, move, recursive ran the most. Timer thread ran a lot as well because we were doing on a timer. And then we can see kind of what took up all our resources. So the ones that ran the most tended to be our make, move, and our advance. And then our hash table put ran a lot as well. If we look at CPU timeline, we can see timer 0 is what's taking up a lot of our CPU. And if we look at our call tree, we can see that every time the timer ran, let's see, it went snake recursive, and kind of rarely it did try move recursive. And if we look at our flame graph, we can see that a lot of our code was doing try move recursive. It goes up to our depth, so this should be 10 times. And this happens often, less often. And almost every time it goes put into a hash map, which takes a lot less time. So you can see that most of the time is taken up by going try move recursive. A bit of the time is going to hash table put. And this gives us some insight into how our app was running. Then our call tree tells us which methods ran. So a recursive method, try move recursive, ran a lot, and it ran less and less often as time went on. And most of the time the timer thread did nothing because we didn't have AI enabled the whole time. And memory usage looks like this, where it just spikes up and then goes down because our AI gradually gathers variables and then throws them away. Our CPU usage was generally constant. If we want to see how inefficient our AI was, we can go into ai.java, for example. We have a silent breakpoint here already. I can go debug, look at overhead, see it's going get X a fair bit, but if I turn on AI, ooh, that's spiking a lot. You can see that our try move recursive is going crazy. We're doing a lot of that. So that is kind of how our breakpoints can help us. We can see which methods take up a lot of time. We can see that get X and try move recursive are being really hammered home, and it's taking almost 8,000 milliseconds just for that. So that is the Java flight recorder and the debugger kind of in action on this. And if we attach the profiler to our app, which we can do even without the flight recorder, let's attach it to a Snake app. We'll attach, let's attach a Java flight recorder to it and let it run for a little bit. That's going to be our little final thing. I'll let the Java flight recorder run a little bit and then show you the results with the AI enabled the whole time. We can just do it for 10 seconds. No CPU sampling data, no call tree. Oh, it's that short. Okay. Well, I guess it was too short of a time, and I didn't start with the flight recorder. But overall, that's how a flight recorder works. That's how breakpoints work. And those are the various techniques we can use to test our code. Not shown in this video, but also useful is the speed tester, which is linked. Well, I'll link it in the description. I'll link it in a little folder about testing. And all of these techniques together, in addition to the speed tester and some programming techniques like dynamic programming, making good use of hash tables and everything, that's what's going to get you towards a winning position on the final assignment, which again is competitive based on how fast your code is. So hopefully that's useful. Hopefully you guys enjoyed. These are some techniques that are hopefully going to prove useful to you, not just now, but also in future classes. And hopefully it's a good way to leave you guys off. Sorry about the glitchy video today. I'll see you guys again on the Best of Comp showcase for this year, which will be opening up soon. And afterwards, I'll see you later. So thank you very much for showing up. Thank you for a great semester, and I'll see you guys later. All right, farewell. And also, if there's any questions, you're welcome to ask now. But I guess I kind of ended it before I asked for questions. Oh well, if you have questions, Piazza, office hours, all available. Office hours will continue to be available in the coming while. Thank you so much, and farewell.